Good morning, good afternoon, good evening, whichever part of the world you're joining us from here today. I am Reza Rokni, and I'm a Google developer advocate specializing on data analytics. And I'm also a contributor and recently a committer to the Apache Beam open source project. And with me, I have Robert.
Hi, I'm Robert Crow. I'm part of the TensorFlow team at Google and specifically focused on TFX and production ML.
Great. So today what we're going to do is Robert is going to go through a high-level overview of TensorFlow Extended and some of its components. And then we're going to look at a very specific use case that I've been working with the TensorFlow Extended team on around time series processing in stream mode, making use of the hermetic seal that exists between the training and the inference path. And Robert will cover that next.
Often, when we first start a machine learning project that is intended for production, we're really focused on our modeling code because, after all, we need a model that produces the result that we need. And that's what research papers are written about, and it's what generates the results that we get for machine learning. But when we move into a production setting, we quickly realize that actually the model that we're developing is a fairly small part of the total amount of code that we need to put our amazing results into production to support it as a product or service. And unfortunately, people have discovered this the hard way. This is kind of a famous tweet now from Gina Blabber at O'Reilly, and it talks about a solution that where they trained the model in something like 3 weeks, which is pretty reasonable. And 11 months later, it's still not deployed because they've discovered all the issues with deploying something into production. So when we start working in production machine learning, we have all the challenges we have in any machine learning development. We need to find a source for labels for our data, assuming we're doing supervised learning. We need to worry about does our data cover our feature space well, and is it the same coverage as the inference requests that we're going to get? We want to minimize dimensionality and maximize the predictive data to try to make it as efficient as possible. We also need to consider issues like fairness and interpretability, which are becoming increasingly important. And in some domains, we have rare conditions. Think of healthcare, for example. You want to be very careful that your model covers really fairly rare conditions that you might not have a lot of data for pretty well. And what this gets to after time, over time, is managing the data lifecycle. But you're putting something into production, that means you have all the same issues you have with any production software deployment. So scalability, is it extensible? Can I extend this thing? How do I manage the configuration? Is it consistent? Is it reproducible? And have I written it in a modular way? Is it something that I can manage in a modular way? And trying to understand what best practices are and maybe defining what those are for my particular use case. Testability. Can I test my code modules? Monitoring it, of course. And safety and security. As we are quickly learning, there are attacks that take place against models, and we need to be aware of that and do what we can to remediate and protect against that. Google has been putting things into production for quite some time, so we've done a lot of research along those lines and written a lot of great papers. So this is a pretty good selection here, going all the way back to 2015. I'd encourage you to take a look at these if you haven't already, and there's some great lessons that can be learned here. So increasingly, this gets around the concept of MLOps, and I think in the conference there's been a lot of discussion about MLOps and what exactly that is. There's different definitions of what it is. So here's a couple of different definitions. The first looks at really understanding and managing communication and collaboration, and managing the production ML lifecycle. So that's certainly, I think, a valid description of what MLOps is. And the second looks at really the factor of automation and quality and focusing on the business and regulatory requirements, which again are also, those are all important aspects of what MLOps needs to be. The CD Foundation, the Continuous Delivery Foundation, has put out an MLOps reference architecture, which is very similar to some of the architectures that you'll see today. It's very similar to what you see in TensorFlow Extended or TFX. There are some differences, obviously, and I have some input into this that I'd like to make a couple of changes, but overall it gives you the basic idea. These are pipelines where they're breaking up different tasks and managing them in a modular way and in a maintainable and monitorable way. So Google's created TensorFlow Extended, TFX, because frankly we've needed it. Google puts machine learning into just about everything that we do. We talk about ourselves as an AI-first company. And you can see, just based on the icons that you can see here, it's in almost all of the Google offerings, really. And this is just a small selection. So TFX is now available as an open source offering for you to use. And we'll be talking about the open source version of it today. TFX has also been adopted by many of our partners, and this is just a fairly small selection of them here. An interesting case is Twitter, where they actually moved from a Torch-based environment that they'd made quite an investment in into TensorFlow, specifically because of some of the advantages they saw in TFX and other parts of the TensorFlow ecosystem. This is at sort of a conceptual level what a TFX pipeline looks like. On the top, you see tasks that you need to perform. So you start with ingesting your data and you proceed through validation and feature engineering and training the model and then validating the model in a very deep way. And then if the model is better than what you have, you're going to push it and serve it. In the middle are libraries, and those libraries are also open sourced, and they're available to use separately. So if you just want to use a particular piece for something that you're working on, you don't have to use all of TFX. In the orange, there are TFX components that make up a pipeline. And these are the standard components that come when you just do a pip install of TFX. And this is sort of the hello world of TFX. This is where you start with a TFX pipeline, and then you can add your own custom components in three different ways, really, to your pipeline to build what you need. So we're not going to talk about all the different components. I just want to mention a couple of important ones for the particular use case that we're looking at today. The first is ExampleGen, where we're going to ingest our data. ExampleGen uses Apache Beam to distribute the processing that it performs across a cluster. So it's going to do a couple of things. It's going to ingest the data, and it's going to split it into your splits, training and eval certainly, or you may have other splits that you want to do. So as you can see, the configuration is very simple for ExampleGen, and there's a number of different formats that are available. There's standard formats that are supported out of the box, and then we have some custom formats where we've provided examples for different approaches to doing a custom format. And then there's a number of different formats that you could take probably the Avro example and use based on support that is available in Apache Beam. And we'll be talking a lot today about Apache Beam. When ExampleGen processes or ingests your data, it's going to do a couple of different things. First of all, it's going to divide your data into spans so that you can work on individual spans one at a time. And in a continuous scenario, it becomes very important to be able to split things into spans. Within each span, you have your splits. So this is showing two different splits, a train and eval split. But obviously, if you had more splits, you'd have more splits here. The next component that we're going to talk about, we're skipping over a couple, is transform. Transform is where you do feature engineering. And again, we're using Apache Beam to distribute that processing across a compute cluster. So the configuration for transform is fairly simple. The code for transform can really be arbitrarily complex because it just depends on what you need for your model and your data, how much feature engineering and what kind of feature engineering you need to do. So this is showing a very simple example where we're just doing a z-score, but we could be, pulling a trained model from a repository and using it to generate embeddings or what have you. This can be arbitrarily complex. And the next component that we want to look at, and again, we're skipping over a bunch, is Bulkinferrer. Normally, you think of a TFX pipeline as primarily being involved with training a model. But for some cases, we're actually running inference in a TFX pipeline, and Bulkinferrer is how we're doing that. So Bulkinferrer, again, is using Apache Beam to distribute this processing over a compute cluster, and it's running inference using a trained model. So that inference uses Apache Beam to run, and there's some support in Beam that we'll talk about in a second. The example that we're looking at is an autoencoder. And in this case, we're using an autoencoder with reconstruction error to do anomaly detection. So an autoencoder looks at learning the data and being able to reconstruct the data. And when the actual data does not match the reconstruction within a certain threshold, that is a way of detecting when you're seeing an anomaly in the actual data. So this is a fairly common approach to doing anomaly detection. And that's the approach that we're going to be using in the use case that we're discussing today. And now I'm going to turn it over to Reza to talk more about our particular use case, and we're going to be having a demo as well. Reza?
Thank you very much, Robert. And TensorFlow Extended makes use of Apache Beam for its data processing. And one of the things I really like about Apache Beam's vision is to allow developers to write in the programming language of their choice, Java, Python, SQL, Go, to be able to build very expressive models, whether it's batch or streaming with the same business logic, to generate the graphs of computation that are then run on the execution environment of their choice, whether that's Spark or other runners. And it would be fantastic if after this talk, folks who are interested would become committers and interested in working with the Apache Beam project to make the runners better. In terms of the Beam model, we have three primitives: a P collection, unordered set of data, and a P transform is a transformation you do on a P collection to generate a new P collection. And then we have the pipeline object, which is a directed acyclic graph for computation. At the bottom, we see a very standard graph, which is very serial here. So we use a read transform to read data to generate our P collection. Then we can do another transformation, for example, inference with run inference from tfx-bsl to generate another P collection, and then a write transform to output the data. So in terms of what we're doing, the project that I've been working with the TFX team on is around time series processing with TFX. And our goal is to try and make use of that hermetic seal that is available between the training and the inference based off the things like TF transform that are pushed into the save model. So here we have Apache Beam reading raw ticks from our time series data. This part of the sample of the application that we put together is in Java. Based off that, it generates a bunch of metrics from that data. So the metrics are sent on to other systems because this library is also for use for other systems for the folks we're working with, as well as generating TensorFlow examples that are landed into Google Cloud Storage and are used in the TFX pipeline for learning. And we can use the Beam pipeline to signal a need to retrain to the TFX pipeline. The TFX pipeline will generate a saved model, which contains the TF transform information, etc., all embedded within that graph. And that is what we use in the final stage on the inference. So I've got two icons here for Apache Beam. We're actually making use of the same business logic for the TensorFlow example generation. But here then we're using the saved model file along with run inference to be able to do inference on that data. And the important part here is the same business logic is being used to generate the metrics that go into TF example, both for training and for inference. In terms of the processing that we're doing, we're actually doing time series processing, which has some interesting challenges when we're doing this in a distributed fashion, where, for example, one of those is gap filling. So the LSTM encoder-decoder needs a dense layer of information in terms of the number of time steps and the number of features. And there are various gaps that we'll see in whether it's market data from financial services or from IoT data. Some of the examples would include when we've seen a value for a specific key, and then suddenly there's no value within a specific time slice, or we may never see a value for a key until later in the life cycle of the pipeline processing. In that example, this is the time series 4, which we see on the, so the time series on the x-axis, the time slices on the y-axis. There's no data points arriving until much later. Or the final type of gap that you can get where you've seen data and then there's suddenly no more data coming. For example, an IoT device that is now broken and will never send information. Or in financial services where you have instruments that are being traded that stop being traded. And if we are doing any gap filling in stream mode, we need ways to be able to stop filling gaps as well as knowing there are gaps to fill. And we use some fairly advanced aspects of the Apache Beam model to achieve this. So we use things like timers to know that a new time interval has arrived, even though there's no data for a specific key. We use things like state to actually be able to take the last known value and make it the value to put in as the default for the current gap. And for if we've never seen a value in the stream and a user wants the ability to generate values until the first value, real value arrives, they can bootstrap the system by sending a key value pair for that particular key that has the initial value to initialize on. And for the final part, for when we want to stop, we have things like time to live. Now, we make use of things like time to live. So time to live is not perfect. It's like, how do you know how long to wait? But it is a mechanism that allows the samples that we're putting together to stop generating information. Okay, so this is a graph of some real data that we processed with our sample library. And these are 3 different instruments from markets that are coming into this as financial data. These 3 instruments are closely correlated together. You see that in the graphs. And the middle graph, the green graph, is less liquid than the others. So there are less data points arriving for it. And what we see in these flat areas, which are very prominent on this side of the graph, the right-hand side, is the gap filling in action. So there have been no data points between these points. The last known value has been used, and this is why we get these flat spots, whereas the other instruments, which are a lot more lively, have a lot more information. In terms of the computations that we do, there are 2 types, type 1 and type 2. And we always do the type 1 because this is a great reducer function. So the type 1 computations that we do on the data, so these essentially become features that are used by that we use in TFX. are things that like max, first, min, sum. So these are all transitive and associative. And if we see these values as data points, we have these fixed windows of time that are occurring, and we are calculating the max for those fixed windows of time. The next type of computation that we do for the time series, which actually gets merged with the first type, is rolling windows. And this is because there are computations where we need the sequence of data, and that's very important. So for example, if you imagine absolute gain, we want to have all of the data that we're processing in sequence for us to do the computation. And a little trick that we use with the modeling there is the sliding window length, in this case, happens to be 2 fixed windows. But importantly, the offset of the sliding window, so when it rolls, is dictated to be exactly the same as the type 1 fixed window computation. What this allows us to do is to merge the data at the end into a dense array for each time slice. And for example, here we have 2 and 3, the absolute gain obviously being 1, then 3 and 1 together become the first value that we send on. So this metric's all being computed in real time on the stream and being sent as TF examples, both to our object store and to our inference. And that's the key part of this. And with that, over to a demo. Great. So for the demo, we're going to make use of the direct runner with Apache Beam, which is the development runner that allows you to do things locally and ensure correctness of your code. And the thing that we're going to be doing is using a synthetic data set. Essentially, it's just a continuous sine wave. So the data that we've already pre-trained with TensorFlow Extended that's generated the saved model for us is this continuous sine wave that's happening with a few features. The data that we're going to send in inference is going to contain some anomalies. So these are values that are clearly outside of the norm for the data we've seen. And the output, and this is actually a result from the output when we process it, essentially picks up on those spikes that we see and generates anomalies in these contiguous blocks. And we'll talk about why there are anomalies across a block and not just one value in a moment. So to show this, I'm afraid we're going to go green screen here. What I'm going to run is I'm going to use the code that's available in the following repository on GitHub. And we're going to run a Gradle command that actually is going to generate some data and the metrics that we discussed earlier. So it's going to do the processing and create TF example files, which contains all of those metrics. We don't actually use all of those metrics within that simple example, but this is good for showing the data engineering needed to make all this work. On the other side, so that will actually send those TF examples to PubSub. It could be Kafka or any other streaming system. On the other side, we have the pipeline that makes use of tfx-bsl's run inference to run inferences against that data. And here you see a bit of the code for what's going to happen on the other side. The pipe is overridden in Python here to mean apply. So pipeline apply transform. And essentially with the Beam pipeline, we're going to use one of the connectors that Rob mentioned, connectors at the start, that reads a string from PubSub. So we are sending this TF example serializer string here. And the next step is a mapping where we're going to parse that into a TF train example object and send it to run inference. Run inference is the API that tfx-bsl provides for us, which is consuming the saved model file that was created in TensorFlow Extended. So I'm going to actually run this using our Gradle command. Essentially, the parameter I'm passing to this is the PubSub topic that we're going to send to. At the beginning, because it's a sliding window, we have to wait a little bit before we get to a count where we get that denseness. So we're ignoring the very first few values. And now it's sending information to PubSub. To run the other command, I'm going to actually just run Python command here, telling it which stream to read from. So on the above, we actually saw an outlier being generated by that data. So as well as the normal data, an outlier has come in. We'll let that model go through for a moment before we go through this. So clearing this up, we're going to get these warnings that are coming up. But the next time an outlier is generated, we should see a block of numbers appear on the demo downstream. So there are some more outliers being generated. And in a moment, the inference will, the model will be perturbed enough to generate a value outside of what we're within the norms that we're expecting, and therefore produce a anomaly session. So any moment now, the demo gods being with us. For some reason, there we are. There we go. So let's cancel this now so we can see this. And this is an outlier has been detected. And if we look at the block of data that is available here, we see values outside of our range, which is normally within the hundreds. And the reason we're getting that block of data is, if you recall from Robert's talk, it's a LSTM, so there are a number of time steps. And when a bad data point comes in, or an anomalous data point comes in, it's going to perturb the model for the duration of those time steps, and that's what this picked up. So that quick demo, which you can go and run yourselves as well, showed the whole process end to end. We are working on the upgraded version to which is 2.23 on a branch, which is a much more sophisticated model and run inference, and that should hopefully be in soon as well. And with that, over to Robert to cover what we've talked about today.
Thanks, Reza. Well, that was an interesting case of using time series with TFX and Apache Beam. And I just want to emphasize that it's one of many use cases that are currently supported in TFX and Apache Beam. We also do, of course, the more mainstream things like image processing and object detection and natural language, as well as things like anomaly detection that we saw here in time series. And you can expand that to be whatever you need it to be. It's open source, and we invite you to contribute. And with that, I hope you enjoyed the talk. Thanks very much, and we'll see you next time.